Hi, everybody, and thanks for joining us for this session, using AI to route energy like data and stabilize the grid. It's with Sean McAvoy from Veritone, and I'm excited to welcome him. But before I do, I just wanted to go over how this session will work, introduce myself, and thank our sponsors as well. So I'm Kathleen Walsh. I'm a managing partner and principal analyst at Modelica. We're an AI-focused research, advisory, and education firm. We also host the very popular AI Today podcast, which is now a top 3 AI-related podcast. You can find that where you listen to all your favorite podcasts, as well as check it out at our Modelica.com website. This event would not be possible without the incredible support of our sponsors and partners, including Allegion, Appen, AWS, Carahsoft, Cloud Factory, Databricks, DataRobot, Labelbox, Microsoft, MTX Group, OmniSci, and Veritone. We're excited to have Veritone here with us at this presentation, and I know that they've given some other live presentations as well, and also have on-demand content. So we encourage you to check out the sponsor pages at dataaiconf.com. You can get a lot of information there about what sponsors do and how they can help you. This conference is for you, and we say this at every session because it really is. We want to make sure that you're getting maximum interaction with all of the sponsors and all of the presenters as well. All live sessions, like the one right now, have a way for you to ask questions. So below the window of the video screen, you'll see that there's an Ask a Question button. You can click on that and type in your questions. And you also have the ability to upvote other people's questions as well. I know a lot of people have been doing it, and it's really helpful to figure out the order that I should ask the question. So please make sure to utilize that. All questions are going to be held until the end of the presentation, but feel free to type them in as they come into your head. The replay videos also have a cool feature where if you type in your question and I click that we're answering it, you can go back in the replay and go right to that Q&A section. So that's why I encourage all of you to type in your question. Questions will be moderated just to make sure that they're appropriate and on topic. In the spirit of maintaining maximum interaction between attendees and presenters, these events are held under Chatham House rule. That means that anybody is free to come to this session and use the information from the discussion, but you're not allowed to reveal who made that comment unless you have specific permission to do so. All live events like this one are recorded and available for instant replay. So I know that we have many folks attending live, but also many folks are watching this on replay. So if you're here on replay, we welcome you as well. It takes about 5 to 10 minutes once we wrap up this session for the replay to be available. If you have any questions at all throughout this event, we encourage you to check out the FAQ section on the dataaiconf.com website. It's a great place to get started and hopefully get most of your questions answered. But I'd like to now introduce our presenter for today, Sean McAvoy of Veritone. He's a seasoned software executive with over 20 plus years of experience in the software industry, and he's worked at companies such as IBM, Dell, Quest, and Symantec. Sean has held executive leadership positions across an array of business units, including customer success, sales, professional services, product management, engineering, and channel development. He's lived in many places, including the US, Europe, and Asia, which is exciting because we have a very international audience. So he's probably lived on many of the continents that you guys are attending from. In his current role, he's a senior vice president at Veritone, and he's responsible for business development for Veritone's artificial intelligence platform. And with that, I would like to now turn it over to Sean. So welcome, Sean.
Thank you very much. And thanks everyone for joining. And one of my roles in terms of looking after business development for the aiWARE platform is I also look after our energy solutions. And in this session, I would like to discuss how Veritone optimizes the grid using predictive AI and intelligent control. Veritone's objective is to make green energy production more predictable, more reliable, and more cost-effective for grid operators. And from our perspective and my perspective, talking to various utility companies and working with them, we see that there's a perfect storm brewing in the energy industry. Today, grid operators are struggling to integrate renewable energy and storage into their legacy infrastructure. And most of this infrastructure is 60, 80 years old. While at the same time, you have demand for energy and consumption of energy is rapidly increasing every single year. And this leads to like more brownouts in terms of like hardware blowing up on the energy grids. I think in the last 10 years has been about $8 billion lost in the US alone, just on infrastructure with things going wrong with the integration of renewable energy resources. And we're also seeing kind of blackouts as well. And especially where I'm based, which is in California, we're kind of starting to get used to that. So our mission, like Veritone's mission, as a leading provider of AI-based energy solutions, is to assist grid operators to reliably and cost-effectively transition to green energy. And I'm going to talk a little bit about the landscape. I like to kind of talk about this in like a story, seeing as I'm Irish and we like to tell stories. So this is a bit of a story. So when we look at the current landscape today, there's about 4 factors that are like impacting the landscape. The first one is like decarbonization. That's like an easy one. We all want to get a greener footprint in our societies. The next one is like decentralization. And this is, you know, today, like renewable energy resources, they're not centralized. They're very much distributed because they need to be in places where they can be positively impacted by the elements. For example, solar panels need to be where the sun is shining. You know, wind turbines need to be somewhere where the wind is blowing all the time. So there's like, there is a decentralization of energy resources. And then we have like democratization. And that really means like anyone today can be a virtual power plant. It is not just utilities anymore that are generating energy. You can have a solar panel on your roof. You can have a Tesla battery, for example, in your garage, and then you can generate and you can store energy and you can sell that energy back to the grid. And this is like, you know, made things a lot more complex and a lot harder to manage, which is why you need more digitization. Distributed energy resources, two-way power require like advanced AI technology solutions. And when you look at like the grid of yesterday, it was extremely simple. I mean, you had one-way power, you had your coal or gas plant, like, you know, centrally located to your city. You would flip the switch, the coal would start burning, and the lights would come on in your house. Very, very simple. But the downsides to that is like it was very expensive because it was very manual to actually run. It is also, as we know, it's environmentally unfriendly, and because of limited availability means it is not sustainable. Fast forward to the kind of electrical grid of today. And here you see it's gotten a lot more complex. You now have distributed energy resources in terms of, you know, adding solar, adding hydro, adding wind. You now have battery storage. You also have microgrids. On the consumption side, there's more electricity being used, like electric vehicles. You have smart homes. You have smart cities. But the pros of adding renewable energy is that it's clean, it's cheaper than fossil fuel. It's also digitized and also democratized. But the cons is like, you know, it's more complex, it is decentralized, and then it becomes like unreliable. And that one word, reliability, is almost like the North Star for our utility companies. They want to have reliability such that when you come home at the end of any day or you go into work, that you have electricity to power all your appliances. So we did just dropping down a little bit deeper into like some of these problems, you know, in terms of green energy and what the problems are associated. The grid has like a new set of problems as you integrate green energy. Number one, it's not predictable. You know, the solar needs the sun to shine. Once it stops like sun shining or cloud cover comes over, you then do not have energy. And the same with wind and the same with hydro. So it needs to become more predictable. It also trying to integrate distributed energy resources into an actual grid. If you're doing it into a legacy grid infrastructure, it becomes complicated because the legacy grid infrastructure was set up for like one-way power. Now we have distributed energy resources, you know, in different places, and they're trying to go through the existing legacy infrastructure, which can cause congestion. And congestion leads to curtailment. And also energy dumping, which that means the utility companies are losing money, and you may not get the energy when you actually need it because it's congested at a substation somewhere. Then you also have like burnouts and blackouts, and this can happen if your distributed energy resources, your green energy, is not being operated effectively and optimally. For example, if cloud cover moves off of a solar panel, for example, and the sun hits it like really hard, and a spike of energy comes down the transmission line, it can blow up like inverters or transformers, or impact like substations or storage batteries. So it needs to be very effectively managed. And another problem is like renewable energy resources have become cheaper, especially solar panels. And now we have a lot of independent operators who they have access to solar, they have access to battery storage, and they want to be able to sell that back to the utilities at the best price. And they need like, advanced high-speed arbitrage solutions to be able to do that, and there's just not a lot of them on the actual market. So now we're going to take a look at Veritone's AI-based energy solutions. So who do we deliver or solve problems to? So we solve problems for utility companies and who definitely need to like optimize grid operations for reliability and cost. We solve problems for the equipment providers who need intelligent predictive device controllers for their inverters, capacitors, transformers. We solve problems for the storage providers who are concerned with optimal dispatch, scheduling, and effective battery management. Because if you think about it, like a lithium battery is actually an explosive device. And then you have independent operators who we just spoke about, who need wholesale arbitrage solutions so that they can actually trade energy on the exchanges in real time. So at a high level, we've broken down the Veritone energy components here. We have like 5 kind of components, or high-level components, and we have more than 20 patents issued against these energy components, and about 10 more patents are actually pending. So the first one on the left-hand side is our forecaster, and this allows us to predict. And we are able to predict like demand, we're able to predict generation, we're able to predict pricing across all types of energy generators. We can also, we have a controller, which is an intelligent controller, which helps manage all of the devices on the grid effectively, and also synchronize all of the devices together as well. We have the Veritone optimizer, which allows us to deploy various strategies onto the grid, which I'll talk a little bit about later. Because really, once you can forecast, once you can control and synchronize, then you can optimize to your heart's content. And we also have like the Veritone arbitrage solution, and this is for the independent operators who are producing and selling energy back to the grid itself. And then lastly, we have our Veritone simulator, which we highly recommend in terms of engagements with software companies. Our simulator allows you to actually try the software and be able to view outcomes before you actually deploy it on your grid environment. Now let's double click down on a number of these. So first one here is our forecaster. So our forecaster helps to predict demand, capacity, and even price at a kilowatt hour level. Like we can predict like 1 minute, 1 hour, 1 week, 1 month in advance, which allows both our software and the actual grid operators to plan in advance. So how do we do this? I mean, to predict, we build models like AI models using historical data and real-time data. So we will build like a model of nodes, which is demand. We will build a model of capacity, also build a model of pricing. We can also build a model of the city that you're actually servicing as well. And we use different forecast models. We probably use about 6 different AI forecast models at any one time. And we always pick the best performing model, because this eliminates like model drift over time, especially when you're using the same type of data set. All of our AI models are They use kind of auto training and adaptation learning, so they get better over time as they start using the data. And just to give you like an example of something that we're able to predict, like, probably one of the most common renewable energy or green energy sources is solar power. And solar power like produces radiation and our kind of solar power. And we're able to kind of predict that out in advance in terms of how much is going to be generated, 1 hour, 1 month, or 1 week in advance. And the way we do it is we will ingest weather data into our software. It could be from ClimateCell, AccuWeather, IBM weather data, or even infrared cameras that we have based directly over the solar panel. And we take a reading of that weather forecast as it sits directly over the solar panel arrays, just using a longitude and latitude of the specific location of the solar arrays. We then combine both the weather predictions and the solar panel capacity and performance into our algorithm, such then that we can then predict in terms of time intervals out how much solar power is going to be generated. And when we think about what we're predicting, we're looking at the weather that is 50 miles out, 30 miles out, 20 miles out, and that equates different time horizons. And once you're able to kind of predict when you're going to start, generating power from the solar panels, you can then prepare the rest of your grid infrastructure. So your inverters are able to, they're warmed up and they're able to ready to actually accept that power. Your battery's able to accept that power without them burning out, which kind of happens a lot we're seeing. And some of these inverters are $1 million, $2 million each. A storage battery can be $15 million. So you don't want to kind of mess with that. And then we move to our predictive controller. So in addition to building, forecast models, we also build AI models for all of the devices that sit on the grid. And that includes your inverters, transformers, capacitors, solar panels, and batteries. And these predictive device controllers, we then integrate them into our smart edge software controls. And our controller incorporates two things. It incorporates forecasts that we just spoke about. And forecast could be, I forecast demand at this level, I forecast, solar panel generation, I forecast price. And then we combine that with rules of industry rules and regulations. So your NERC and FERC rules. Also, rules around the device that you're trying to control, which would be warranty rules and also operating parameters of the actual device itself. And of course, regulatory compliance. And this allows our smart controllers to make autonomous decisions in real time. For example, whether to ramp up an inverter to kind of ramp up or ramp down, its production. And our AI decision system is distributed. It is not centralized. And so we use a Hamiltonian approach for our AI decision making, which allows our controllers to make autonomous decisions at the edge. And we also use what's called active synchronization, for dynamic systems, where all of the devices that are on the actual grid under our control, they're synchronized with each other, and they're also synchronized with the grid. So our controllers know at any one time the state of what every other device is, and also the state of the grid, so it can make much better decisions over time. The next one is our optimizer. This is the cool one. So, once you, as I said kind of earlier, once you're able to forecast, once you're able to control, once you're able to synchronize, then you can deploy optimization strategies. And we can optimize the grid for, energy, what I call kind of energy quality, which is you're looking at VAR control, you're looking at frequency regulation, solar smoothing, especially on frequency regulation. All of our grids in the US, they run at kind of, 60 hertz. I think in Europe, it's at 50 hertz. And if you're not producing kind of power at the same level as the grid, which is 60 hertz, and you're pumping in, say, something that's at like 55 hertz, for the US, then the appliances in someone's home is just not going to work. So we have to kind of make sure that that kind of works like at all time, and we will optimize for that. I mean, we also optimize for cost, we can optimize for compliance, we can optimize for usage. So in the picture here, like you can optimize for what I call optimal economic usage. So, if you know the price of your kilowatt hour, and you know what is generating at any one time, you can say, okay, I want to use the best cost strategy, which means I may take 40% of my solar, I'm going to take 25% of my wind, and about 35% of actual storage. And then, like, to avoid congestion, we can route that energy, with an optimal path algorithm to get to the substation that it needs to get at, which again avoids congestion and avoids kind of energy dumping. So optimization strategies are pretty cool to work with and deploy. And this is where the grids and utilities get a lot of cost savings from our software, and also they increase reliability to their end customers. Our next one here is the arbitrage software. Like, for those people who are into wholesale selling of kind of bulk energy to the exchanges, especially those in the US. We're currently working with a company on the ERCOT exchange in Texas. This is going to be kind of very interesting to you. So, like, in my opinion, I've been talking to a lot of different independent operators. Their feedback is that, like, current arbitrage solutions lack the ability to fuse risk, to fuse like dispatch and demand with market and weather uncertainty, like in real time. And we're able to solve for this. Our arbitrage solution was originally developed for high-speed trading in banks, and we originally sold this to, I think, like Citigroup. And since then, we have transformed this into be able to do arbitrage for energy. And our arbitrage solution is completely automated and is very autonomous. And it is based on like short-term risk forecasting and optimized dispatch decision-making. And we have a lot of interest in this software from the independent operators, which are springing up like now all over the place because of the democratization of energy. And lastly, here we have our simulator. So again, like I spoke about this earlier, we recommend like definitely using a simulator that allows you, it just reduces your overall risk of an engagement. It minimizes cost, achieves faster outcomes. Our simulator like incorporates all of our AI energy solution modules like forecaster, controller, optimizer, even say synchronization. And we also do optimal economic dispatch as well. And you can determine outcomes like once it is provided with sensory data. And we don't need a huge amount of data to actually create a model and show someone like what potential outcomes could actually be. Now we're just going to get into deployment, which is one slide, and it's the last slide. And a lot of people ask us, and especially government people who we deal with, the Department of Energy, or you have utility companies want to know how they can deploy it. Some have security regulations that we have to adhere to. So we can deploy our software energy solutions in the cloud, or we can do them 100% on premise. We can do a hybrid of those approach. Our software will, it'll run in AWS cloud, also in Azure, and we are FedRAMP certified as well, which allows us to work with the Department of Energy across multiple of the Army and Air Force bases today. So that is the end of my presentation, and I'll hand it back for any questions.
All right. Well, thank you, Sean. That was awesome. I'm just going to get you back on screen. I know that I have a bunch of questions from that presentation, and it's interesting because, Sean and I were talking earlier, and he said that this might be a little bit different topic that is being presented, but we want to make sure that we have, a well-rounded conference that talks about, all aspects of data usage. So I wanted to start by asking the question, how are traditional energy companies embracing AI? And then how are you guys helping them?
So the traditional ones are, they're embracing it slowly. They're taking like bite-sized chunks. But what's kind of pushing them to do this is regulation coming from the governments saying that you must have X amount of your energy produced using green energy, number one. So regulation is key there. Number two is that as they're adding like more and more distributed energy resources, they're feeling the pain in terms of how do I better manage this? How do I predict? This cannot be manual anymore. And how do I create autonomous decision-making locally, right beside the actual device that is being used? For example, like a battery, like the max kind of round trip actions or orders has to be like less than 170 milliseconds or the battery could actually blow up. So they're looking for AI to do a lot of prediction, to do a lot of synchronization, but it's definitely around regulation is driving them. Also, as they're making mistakes and they're expanding their operations, is getting more complex. And that's why they're looking more towards AI to actually do it, to automate the process. Did that answer your question?
Yes, that was great. Thank you so much. Now we have another question from someone in the audience. What if I have a physical model in Modelica or Simulink that I want to integrate? Can I do that?
Yes, you can. So our simulator is actually developed using Simulink and MATLAB. So we can actually pull in like all the models that they actually have in there today. Or if you have one yourself, you can add it to Simulink, and then we can actually leverage that within our simulator today. And we love that because we don't have to create the model. If somebody has, an inverter that we have never used before, and there's a model already created in Simulink, we just leverage that straight away, and it cuts down the time of generating the model. So good question, and yes, we can. Great.
We have another question as well. What different AI forecasting methods are used?
So that means like getting down into the specific algorithms around how we do our forecasting, which I don't really want to share like a lot of that probably on this call. That's like some of our secret sauce in terms of how we do our forecasting. I can only say like at a high level, we do use probably 6 different forecasting algorithms at any one time, and we swap them out, regularly based on the highest performing one, because we're always concerned with model bias and also with model drift. That's as far as I can go in terms of talking about like which algorithms we actually use.
Sure. Yeah, totally understand. We got a follow-up question with that. What weather sites are used? Can you share that?
Yeah, I can share that. So IBM weather data. So the weather company was bought by IBM. So we work a lot with the IBM weather company. We also work with ClimateCell, who is another one, and also AccuWeather. And there's also NOAA that you can also use, which is kind of free. And if you want to get like really like precise down to the actual square footage of where your kind of solar panels are, you might want to think about using the infrared cameras, which you can stick like a 40-foot pole in the ground and put like 2 180-degree infrared cameras and take that feed, and they can like look out and to be able to calculate through thermal imaging like what type of weather patterns are coming in. So all of the above we'll use, and some of them are better in some regions than others in terms of coverage. So you have to have kind of an array of forecast weather types at your disposal, depending on where your renewable energy resources are based.
Great, thanks for answering that. We have another specific question from the audience as well. Can I use MATLAB optimization with your optimizer?
Yes, you can. That's not a problem.
Okay, that was an easy question and answer.
MATLAB is really cool in terms of like being able to being able to integrate like optimizations like already there and available. So we love that stuff.
Are you able to describe a little bit more about your optimization?
So optimization, we use. I'll tell you, we use Pareto game theory for our optimization. So that's one giveaway right there. We also use Sharp ratio, which is another one. We use that mainly in arbitrage. So these are commonly available, both Pareto and Sharp ratio. So, I'm not hiding anything there. And but our main thing that we do is for optimization is we use a Hamiltonian approach. And a Hamiltonian approach is it distributes the problem solving down into like individual bite-sized sub problems that are able to be solved like autonomously and locally themselves. And the Hamiltonian models that we actually create, they're able to communicate back to each other via, we have this Blackboard architecture where the models will communicate back and forth what their state is, so that the other models, like, they're constantly updated all the time with the states from the other Hamiltonian models throughout the actual system. And what that does, which is key, is unlike kind of like, neural networks where you need huge amounts of data, large amounts of like GPU power, we don't need that because we're breaking down a problem into bite-sized chunks. And for example, we would have, a Hamiltonian model built around an inverter, and our controller will be connected to that inverter. And that controller will do autonomous decision-making in real time right at that inverter, and we can put it on a Raspberry Pi and plug it into the actual inverter. And so that also allows you to synchronize in real time as well. It allows you to optimize in real time. So, we have a couple of papers already released on our Hamiltonian approach to problem solving, which traverses not just energy, but we also use it in healthcare as well, and also cyber security.
Great. If people want to get a hold of those papers, are they on your website?
They are on the website, yes. Some of them, a bunch of them are on the website today. If not, just email me and I'll just like point you in the right direction. There's a whole bunch of them on the IEEE site, probably around 20, I think, on that site that have been published on IEEE. You can also like search for Veritone patents, and the energy patents are also available if you want to look at them. They've got great descriptions at the front of at the beginning of the patents, which describe the technology that we're actually using, and we have about 20 issued patents at this stage.
Awesome. Thank you for sharing that. I know that we have a few other questions as well, talking about the weather data that you've used. Is that free data?
No, it's, well, let me take that back. The NOAA data is free data. But when you get into asking for data for specific locations and, 20 different variables, because you're looking for cloud density, cloud height, you're looking for humidity, you're looking for temperature, etc., barometric pressure, you have to pay for that service. And the services are all different. They have different packages based on the type of data you want for a particular region, also how far back you want the actual data, what APIs you want to access. So they have, they'll have like APIs for actual forecasting themselves. They'll have APIs for current weather, so it depends on the packages you want, but you can go to any of those sites. But to be able to use it in a production environment, you will need to pay for the service.
Okay, that's great to know. I think, the casual user may not go into this, but if they're looking to do it on a more, broader scale, then that's
casual users should probably go to NOAA, I would say, because you can get that for free, even though
it's probably a great place to start. Can your AI determine if the power blackouts are coming from an attack that's being executed on the grid itself, or is it more monitoring energy for efficiency purposes?
You can. So we use, in terms of like attacks, we use anomaly detection. I didn't speak about that in this presentation because it's more aligned to kind of like our cybersecurity efforts. So we use like anomaly detection, AI, and you're looking for like anomalies happening like across the transmission lines or at the substations in terms of, we expect demand to be this, we expect, normal is like this amount of kilowatt or power, like traversing the transmission. And then once we start detecting anomalies, we can build up a pattern. We can do alerting on that. But more importantly, you can do islanding. So you can start to shut off and reroute, power to different substations if you think one is has been kind of, compromised.
Okay, great. And then I wanted to kind of ask a more general question. AI is being used to help monitor and optimize for energy availability, production costs, and more, which when you had your energy optimization slide, you touched upon. So can you share with us some examples of savings that customers have had?
Sure. The biggest one we find, this is general one, is if you can kind of optimally operate a renewable energy grid, then because it's cheaper and you do not have to use as much fossil fuels or you're spinning reserves, you can then pass those cost savings on to your end customers. That is, when I speak to utility companies, that's the first thing they ask me. How can I pass on more cost savings to my end customers? We have a very interesting project that we're doing right now, which I'll also talk about let's call it like behind the meter. So all the utilities are for the meter, then you go behind the meter, so residential. So we're working right now with a company who they have like 2,700 homes, residential homes in this development. Each of them have a solar panel on the roof, and they also have a battery in their garage. And what they're doing is that they are, instead of selling their energy that they don't use during the middle of the day back to the grid, they're storing it in their batteries that are in their houses, and then they're aggregating. So we're synchronizing all of these batteries via our controllers, and then what we're able to do is we're able to go back to the grid and be able to tell them, or a utility company, and say, we have this much bulk energy. And because we do forecasting and predictability, we can actually tell the utility company, we will have that tomorrow. And the grids love this because they're like, okay, well, these are trustworthy people. I can turn off my coal burning plant right now and save tons of money. But on the residential side, the homes, you're putting like that power of, what will I do with my excess energy? They can either use it to sell back to the grid at a very good price because they're selling in bulk and they're able to do a day ahead commit, or they can use that energy themselves to offset their energy needs at peak times during the day, which is either in the morning or in the evening. So that's kind of like two kind of cost saving ways to look at it, both from the utility side but also from, say, residential side as well.
That's really interesting. Speaking about that, I know that typically in residential homes, Monday through Friday, people are not in the home as much, but with COVID, we are in our homes a lot more. Have you seen energy consumption change in that regard?
Yes and no. It's like a lot more people are working from home and they're using energy there, but then you have the offices are not being used. So you're kind of like have this like balancing effect, out. So the big problem is that what we're seeing is like a lot of states in the U.S. I'll take the U.S. example, and let's take even California. They were dependent on their neighboring states to supply them with energy when they had needs, and that's more along the arbitrage. But when you have climate change, for example, like we are experiencing in the U.S., and then all your neighbors are affected as well, such that we had like 2 weeks ago in California, we had a massive heat wave that not only like affected California, but also the neighboring states as well. So they did not have the energy to give California, therefore California suffered rolling blackouts. So, COVID has like impacted in terms of like more people working from home, but then we're not using as much on the industrial and commercial side either. So sorry, I kind of mixed up like a couple of different scenarios there.
That's okay. I was thinking specifically when you were talking about the residential neighborhoods, having that extra consumption and now being able to sell it back. I think sometimes maybe they don't have that extra consumption and they're using it, or they don't have that extra energy to sell and they're just kind of, using it themselves. So we do have one more question from the audience maybe we can get to. Have you done anything with hydraulic pumped storage so that power plants do not need to idle?
We have not done anything significant in that area, but we like that I can talk about. We're doing one with, I mean, like not on the, let's call it the commercial side, but we are doing one on, let's call it the government side, on one of the Army bases. And unfortunately, I can't talk much more about that, but it is definitely along the lines of what you're actually saying. Idling means you're consuming power unnecessarily. And there are ways to optimize around that. But when you're dealing with doing it at the government level, we can't really speak to it.
Fair enough. I know that maybe if you guys want to chat offline,
yeah, that's fine. Yeah,
reach out to Sean directly,
yeah,
or the Veritone team again at that sponsor page. I know that there's been a few other people who have been very engaged throughout this entire presentation, and I do really encourage you to reach out to Sean directly, reach out to the Veritone team. I'm sure that, you could take advantage of some one-on-one time with them, schedule that out. And again, check out their page so that you can directly contact them. Sean, I want to thank you so much for this presentation. It was incredible. I know we got a lot of engagement from the audience. And if anybody's watching this on replay and you didn't get a chance to ask your questions live, please do go check out the Veritone sponsor page so you can reach out to them.
Thank you all.
Bye, Sean.
Bye.